Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong. Each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field, all these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, It's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason. It has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the sun, the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the sun is just one node, a lone star among countless others. Close to the sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the sun. Although the sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness, and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of a galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our sun is now. But even stars like our sun must face change. In about 5 billion years, the sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? Threads that weave the complex fabric of the universe. The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet, it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder: what other mysteries does the universe hold that we have yet to unravel? Imagine a burst of energy so powerful that it eclipsed an entire galaxy for a moment. A burst of unimaginable power that traveled billions of light years to reach us, whose origin is still shrouded in mystery. It's not simply some sort of science fiction. It's the true story of gamma ray bursts, the most energetic events known in the universe. On October 9th, 2022, astronomers discovered something unprecedented, the brightest gamma-ray burst of all time, which they nicknamed BOAT. It was so unusual that it shook nearly all of their previous concepts about these cosmic phenomena. But the story of GRB 2210-09A is not just about brightness, it's about the questions it raises, anomalies in its spectrum, the unexpected absence of heavy elements, and new challenges to our understanding of how the most powerful explosions in the universe happen. What caused this colossal explosion? And what secrets can it reveal about the forces shaping our universe? The universe is a realm of unusual phenomena, some of which challenge the very limits of our understanding. Prominent among them are gamma-ray bursts, GRBs, some of the most powerful and mysterious explosions known to science. Discovered quite by accident in 1967 by U.S. military satellites, gamma-ray bursts were at first a puzzling mystery and cause for concern because of their intense energy release, which were mistaken for nuclear testing. However, as it became clear that their origin was from somewhere in the cosmos, GRBs quickly evolved from being a top-secret mystery to one of the most studied astrophysical phenomena. These bursts are divided into two main types: short GRBs, which last less than 2 seconds, and long GRBs, which can last up to several minutes. This division is not merely academic. It reflects the different underlying physical processes. Short GRBs are usually associated with neutron-star collisions. While long GRBs, like the one observed in October 2022, are associated with a cataclysmic collapse of massive stars. The event in question, dubbed brightest of all time, or BOAT, occurred in the constellation Sagitta. Detected on October 9, 2022, this gamma-ray burst was unlike anything astronomers had ever before observed. Its brightness, 10 times greater than all previously recorded GRBs, shocked the scientific community. What made this event even more amazing was its duration. It lasted 10 minutes, and the afterglow was visible for more than 10 hours. Most outbursts disappear from view within a few seconds or minutes, making BOAT an exceptional event. But beyond the spectacle, the BOAT event has profound implications for our understanding of the universe. Gamma-ray bursts are, by their very nature, windows into extreme conditions that cannot be replicated on Earth. They allow scientists to investigate the fundamental laws of physics, especially when matter is subjected to intense energy and gravitational forces. The BOAT event, so bright and so close, provided a unique opportunity to study these extreme conditions in unprecedented detail. The resulting data opens new avenues for understanding not only gamma-ray bursts, but also the very processes that govern the life and death of stars. The brightest of all time, GRB 2210-09A, then stood out not only for its staggering intensity, but also for its amazing duration. The explosion was so powerful that it was the brightest gamma-ray burst ever recorded, lasted 10 minutes, and left an afterglow visible for more than 10 hours. Such an event at a distance of only 2.4 billion light-years is not just rare, it's almost unprecedented, occurring only once every 10,000 years. What makes this outburst truly unique is the combination of extreme brightness and prolonged visibility. Most GRBs are fleeting, often only detectable for a few seconds or minutes. In contrast, GRB 2210-09A lasted much longer. High-energy emissions lasted for tens of thousands of seconds. This duration provided an unprecedented opportunity for observations and analysis over a wide wavelength spectrum, from X-rays to gamma rays. The boat brightness was so intense that it caused saturation effects in numerous scientific instruments, including the GBM, Gamma Burst Monitor, and LAT, Large Area Telescope. These instruments, designed to capture and analyze high-energy photons, were overwhelmed by the power of the event, resulting in significant noise and data delays. Notably, the 400 GeV, Giga-Electron Volt photon, was detected nearly 10 hours after the initial burst, indicating unusually high energy levels. Despite its stunning brightness and duration, this event also presented us with significant challenges. Spectral analysis showed that the peak energy of the flare reached about 15 MeV, mega-electron volts, at the very beginning of the event, gradually decreasing over time. However, part of what puzzled scientists was the discovery of a boat-related supernova, which turned out to be surprisingly ordinary. Given the extreme nature of the GRB, one might expect its progenitor supernova to be equally extraordinary. Instead, the detected supernova turned out to be almost completely unremarkable. It even lacked signs of heavy elements, which are usually associated with such powerful explosions. But more on that later. This unexpected discovery has led to several hypotheses, one of which suggests that the relative position of the Earth to the GRB may have played a crucial role in the concentrated detection of gamma rays. The narrow jets emitted during the explosion were likely pointed almost perfectly toward Earth, making the event appear much more intense than if the jets were slightly off-axis. This alignment, combined with the GRB's power, created the perfect storm that resulted in Boat being recorded as the brightest GRB ever observed. In addition, the detection of such high-energy photons raises intriguing questions about the mechanisms of radiation. Conventional models can't fully explain the observed unusual energy levels, leading some researchers to consider the possibility of new physics, such as interactions with dark matter particles. While these ideas remain speculative, they highlight the potential of GRB 221009A to expand our understanding of the universe in directions we have yet to fully comprehend. The formation of gamma-ray bursts is closely intertwined with the life cycle of massive stars. When a star, several times the mass of the Sun, exhausts its nuclear fuel, its core can no longer support the weight of the outer layers. This catastrophic collapse leads to a supernova explosion. But in some stars, it also leads to the formation of an incredibly dense black hole. When matter from a collapsing star falls into a black hole, strong magnetic fields turn some of that matter into narrow, focused jets that fly outward at nearly the speed of light. These jets are the engines of gamma-ray bursts, and their orientation relative to the Earth determines whether we can observe GRBs. In the case of the Boat event, the jets were particularly narrow and pointed almost directly at Earth. Normally, GRB jets scatter somewhat as they pass through space, but in the Boat event, the jets remained exceptionally concentrated, focusing their enormous energy into a relatively smaller area, resulting in a more intense emission. The influence of these jets extends far beyond the place of their origin. When 221009A erupted, its intense gamma rays reached the Earth and interacted with our planet's atmosphere in surprising ways. One of the most significant effects was a temporary compression of the Earth's ionosphere, a layer of the atmosphere containing a high concentration of ions and free electrons. This compression was akin to the effect caused by a large solar flare when the ionosphere is bombarded by solar particles, causing communication systems and satellites to malfunction. However, the gamma rays from the Boat event were much more energetic than those normally associated with solar flares. The energy of the burst was enough to cause noticeable changes in the ionosphere, even at altitudes where such interactions rarely occur. Observatories around the world quickly detected these changes, leading to a flurry of data analysis to understand the full impact of the GRB on Earth's atmosphere. The data collected during this event has given scientists new insights into how such bursts can affect planetary atmospheres, especially the interaction of high-energy photons and their potential to affect atmospheric chemistry and dynamics. At the chemical level, gamma rays triggered reactions in the atmosphere that produced additional nitrogen oxide and other reactive nitrogen species. These molecules play a critical role in ozone chemistry, particularly in the destruction of ozone in the upper atmosphere. Although the exact effect both had on global ozone levels hasn't yet been studied, such bursts may contribute to local or temporary changes in ozone concentration, potentially affecting the protection of the atmosphere from harmful ultraviolet radiation. However, these observations have also raised new questions. The unprecedented strength and narrowness of the boat event jets challenge existing models of GRB formation and propagation. Standard models predict a certain degree of jet spread, which helps disperse energy over a wider area. But the boat event jets have disproved these expectations, suggesting that under certain conditions, jets can remain tightly focused over much greater distances than previously thought. According to modern ideas, the extreme energy and rapid rotation of the collapsing star played a key role in this. The intense magnetic fields produced by the star's rotation probably contributed to the collimation of the jets, preventing them from spreading out in space. In addition, the lack of significant interference from surrounding matter may have allowed the jets to maintain their tight focus over vast distances. These findings not only challenge our current models, but also hint at the possibility of previously undetected GRBs with similarly focused jets that may have been missed by our instruments due to their directional nature. A better understanding of these mechanisms may reveal new classes of GRBs and their potential impact on both the local environment and distant planets, including Earth. However, let's return to the question of how our outburst is related to the formation of elements in the universe. It's simple. The formation of elements in the universe is history written in the hearts of stars. Inside a star, nuclear fusion works like a cosmic forge, turning light elements, such as hydrogen and helium, into increasingly heavier elements. This process continues until the element iron is formed. At this point, the fusion process no longer releases energy. It requires more energy than it produces, leading to a catastrophic imbalance. The star can no longer support its weight, leading to its eventual collapse, and often to a supernova explosion. While fusion in stars easily produces elements up to iron, much more extreme conditions are required to create elements heavier than iron, such as gold. These heavier elements are formed primarily by a process known as fast neutron capture, or R process. During the R process, the dense environment with a high neutron flux allows atomic nuclei to rapidly capture neutrons, creating increasingly heavier elements in a very short time. This process is best known in neutron-star collisions, where the enormous energy and neutron-rich environment create ideal conditions for the R process to occur. However, neutron-star collisions are not the only cosmic events that can produce heavy elements. Another potential site for R process nucleosynthesis is the collapse of massive, rapidly rotating stars into black holes, events known as collapsars. In these scenarios, intense magnetic fields and rapid rotation can drive powerful jets that contribute to the R process, potentially creating significant amounts of heavy elements such as gold and platinum. But when scientists pointed their instruments at the boat event, they were surprised to note something conspicuously missing. Despite the extreme energy and conditions seemingly ripe for nucleosynthesis in the R process, no evidence of heavy elements was detected in the supernova spectrum. No gold, no platinum, none of the things one would expect from such a powerful event. This absence raises important questions about our understanding of how and where the heaviest elements in the universe are formed. This surprising result leads to the thought that not all collapsars are prolific producers of heavy elements. Perhaps the conditions required for significant nucleosynthesis in the R process are even more specific than we thought, and may only occur under certain conditions within these already rare events. On the other hand, this could mean that other processes or conditions related to neutron-star mergers play a more significant role in enriching the universe with heavy elements. Another interesting thing about Brightest of All Time is that it may well shed some light on the nature of dark matter. According to one intriguing hypothesis, dark matter may consist of particles called axions, hypothetical particles that have not yet been directly observed. The idea that photons, particles of light, can turn into axions as they travel through space is a tantalizing one. If true, it could help explain why dark matter is so hard to detect. Perhaps it's hiding in plain sight in the form of photons that can turn into axions and elude our instruments. The boat event, with its intense burst of gamma rays, provides a unique opportunity to explore this hypothesis. As these gamma rays spread across the vastness of space, some of them may have interacted with cosmic magnetic fields, becoming axions. This process could reduce the flux of gamma rays reaching Earth, a subtle signal that could hint at the presence of axions. Although no definitive evidence for the existence of axions was found in the boat event data, this possibility remains an interesting avenue for further research. If future observations of such events reveal patterns consistent with the conversion of photons into axions, this could be a breakthrough in our understanding of dark matter and open the door to new physics beyond the standard model. As we look to the future of astrophysics, the study of gamma-ray bursts remains a cutting-edge frontier full of promise and mystery. Current missions such as NASA's Fermi Gamma-Ray Space Telescope and the European Space Agency's Integral continue to play a critical role in directing and analyzing GRBs. But the next generation of missions will push these boundaries even further. Projects such as the Sino-French SVOM mission and NASA's upcoming COSY mission are designed to provide unprecedented insight into the high-energy universe. These missions will aim to detect the most extreme cosmic events and will allow us to collect data with greater precision, potentially unlocking new physics and deepening our understanding of the mechanisms behind these powerful explosions. Will future observations reveal the elusive nature of axions, or perhaps identify the specific conditions under which the heaviest elements are formed? These are the questions that define the next steps in the exploration of the universe, guiding us toward a deeper understanding of the cosmos and our place in it. Events such as BOAT serve as milestones in the development of astrophysics, reminding us that the universe is much more complex and dynamic than we can currently understand. Each discovery forces us to ask new questions and propels our quest for knowledge forward. And who knows, perhaps the answers to these mysteries are just a cosmic explosion away and are waiting to be uncovered by curious minds. In the meantime, we'll continue to keep you up to date with new developments. Stay inquisitive, and until next time, imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It's a marvel not only of engineering but also of ambition, a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, known as CERN, They represent the gateway to revolutionary discoveries. Here, the concepts of time, space, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics. It's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe, but is nestled in the beautiful landscapes of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge, and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground. The Large Hadron Collider, or LHC. This outstanding example of human ingenuity is 17 miles in circumference, and it's where some of the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang by accelerating particles to near light speeds and colliding them with each other. The LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it's also a hotbed of technological advances. Innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows scientists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it's not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi elements of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension like in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These phenomena, predicted by the same string theory, would be extremely short-lived and would not pose a threat to our existence, as the sensational news of the yellow press suggests. While in pop culture, portals may be portrayed as doors to alternate realities or times, in the world of high-energy physics, they represent an opportunity to observe and study conditions and particles that can barely exist in the natural universe. These experiments have the potential to open up new dimensions of physics. Literally, by analyzing the particles produced by these collisions, scientists can gather evidence that either confirms these theories or sends them back to the drawing board. With its unprecedented ability to test these theories, the LHC acts like a giant microscope, magnifying the very fabric of the universe and helping us understand the fundamental principles that govern everything we see and everything we don't. Particle physics is constantly evolving, and each experiment and discovery pushes the boundaries of our understanding of the universe. From discovering fundamental particles to challenging the limits of physics, the achievements of this research center are monumental. At the center of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to elementary particles. Discovered in 2012, this breakthrough confirmed a crucial part of the standard model of particle physics and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, often called the God particle, has answered fundamental questions about how particles acquire mass. This discovery was a triumph of theoretical physics. Also of note is the recent public release of the discovery of the Higgs boson by the CMS collaboration, which marks a significant commitment to open science and collaborative research. Transparency fosters a global scientific dialogue in which hypotheses can be rigorously tested and new theories can emerge from shared knowledge. This release, which includes the unique combined software developed to search for the Higgs boson, allows scientists around the world to explore the intricate details of this monumental discovery. The resulting likelihood function with nearly 700 parameters captures the complexity of the experimental data, offering a multi-dimensional representation that defies even the most sophisticated visualizations. This openness not only democratizes access to cutting-edge science, but also enhances the collective ability to validate and build on key findings. But the journey didn't end there. CERN has played a key role in other significant discoveries, such as the isolation of antimatter and the detailed study of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Another experiment called ALPHA has successfully trapped antihydrogen atoms, opening a new way to study the properties of antimatter. This pioneering work aims to answer the question of why the universe is made up mostly of matter, even though the Big Bang theory suggests that there's an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By studying quark-gluon interactions, scientists are delving into the study of the strong force, the fundamental force that holds atomic nuclei together. Each discovery at CERN not only adds a new layer to our understanding of particle physics, but can also push the boundaries of what technology can achieve under such extreme conditions. These experiments require the precise coordination of hundreds of scientists and cutting-edge technology, reflecting the amazing collaboration of people around the world. As you may have realized by now, the LHC is not just a technology loop. It's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding beams of protons into the collider with a chain of small gas pedals. Each proton begins its journey in a simple bottle of hydrogen, where electrons are stripped from it, leaving bare protons ready for acceleration. These protons pass through a series of gas pedals, gaining energy at each stage until they finally arrive at the LHC. Once in the collider, the proton beams are boosted to finite energy levels, reaching the 6.8 tera-electron-volt mark during the latest 2024 launches. This intense energy is necessary for the protons to collide with sufficient force to decay into a range of subatomic particles, some of which may never have been observed before. The whole process takes place on a scale that's difficult to comprehend with everyday analogies, but we'll still try to explain the concept fully. 1 tera-electron-volt is roughly equal to the kinetic energy of a flying mosquito. Thus, 6.8 TeV is akin to the total energy of about 6.8 flying mosquitoes. However, this energy is packed into a particle that is inconceivably smaller than a mosquito. The proton is a subatomic particle, meaning it's part of the nucleus of an atom, and has a diameter of about 1 femtometer. By comparison, a mosquito was about 1/4 inch long. So, to visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a large skyscraper. But all the energy of a moving skyscraper would be packed into such a small object. So let's continue. Of crucial importance in the whole process is the achievement of proton beam stability, a state when the beams are dense and well-focused. The beams are carefully regulated or squeezed to ensure that they collide in the detectors at the points where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at unprecedented energy levels in 2024, marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 tera-electron-volts at even higher luminosities than before, meaning more collisions for data-gathering experiments. This phase will be followed by experiments with lead ions, providing a different set of conditions to study. Also this year, the ATLAS experiment has already achieved a milestone in particle physics by measuring the width of the W boson for the first time. This parameter, crucial for understanding the weak force carried by the W boson, was found to be 2,202 mega-electron-volt, which agrees well with the predictions of the Standard Model. Moreover, at the forefront of investigating the fundamental asymmetries of our universe, the LHCb collaboration has made significant progress in understanding the complex interplay between matter and antimatter. In recent experiments, they've studied the behavior of the neutral D mesons and neutral strange B mesons, uncovering new layers of complexity in how these particles violate charge parity symmetry. The neutral D meson, consisting of a charm quark and an up antiquark, has shown a peculiar quantum quirk. It can spontaneously transform into its antimatter counterpart and back again. This phenomena has been captured with unprecedented precision in recent data sets from the first 2 LHC runs. The current study aims to identify potential CP violations in these transformations, which may shed light on the predominance of matter over antimatter in our universe. Similarly, the neutral strange B meson, consisting of a bottom antiquark and a strange quark, showed time-dependent CP violations when decaying into charged kaons. This observation marks a significant advance, as it was achieved with statistical significance beyond the typical discovery threshold in particle physics. These results not only confirm the known behavior of these particles, but also open new avenues of research. With the LHC now operating at higher luminosities, future data could further refine these measurements, potentially leading to new physics beyond the standard model that could explain dark matter and matter-antimatter asymmetry. In the vast universe of information surrounding the Large Hadron Collider, many myths and sensational stories have taken root. Today we'll try to clear up these misconceptions and explore the real scientific picture going on deep beneath the surface. One common myth is that experiments at the collider can inadvertently produce black holes capable of consuming the Earth. While the LHC can create tiny black holes, they're on the quantum scale and evaporate almost instantly through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these microscopic black holes pose no danger. They provide a fascinating insight into gravitational forces, but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic claim is that the collider opens portals to other dimensions, or causes catastrophic natural disasters. Such scenarios, although popular in movies and on television, are not supported by any scientific evidence. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN operates under strict safety protocols. Comprehensive checks and risk assessments are carried out regularly to ensure that all experiments are safe, not only for scientists, but also for the environment. Finally, stories of supernatural phenomena or secret experiments are completely unfounded. As a transparent scientific organization, its research is published and available to the global scientific community. The commitment to openness extends to public documentation, accessible databases, and collaborative projects across continents. As we continue our journey, we want to remind ourselves to remember to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multidimensional research at CERN, we are exploring concepts that push the boundaries of our understanding of the universe. This area of physics considers the possibility that our universe may not be limited to the 3 dimensions of space and 1 of time that we experience every day. The idea of higher dimensions comes from theories such as string theory and superstring theory, which suggests that particles are not zero-dimensional points, but rather one-dimensional strings vibrating in multi-dimensional space. These theories suggest the existence of up to 10 or 11 dimensions, which may help resolve inconsistencies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to investigate these higher dimensions indirectly. One approach is to look for signs of particles that may exist only in these higher dimensions, or effects, such as the formation of microscopic black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they may explain why gravity is much weaker than other fundamental forces. Beyond theoretical curiosity, the study of higher dimensions can lead to technological advances in fields such as quantum computing and materials science, as these concepts push the development of new technologies to detect and measure extremely small and fast phenomena. As we delve deeper into the uncharted frontiers of particle physics, a new CERN initiative, the Search for Hidden Particles Project, or SHIP, is poised to revolutionize our understanding of the cosmos. This ambitious project aims to detect elusive ghost particles that may hint at higher dimensions beyond our three-dimensional space. The SHIP experiment is based on an innovative concept. Unlike traditional collisions of the LHC, where particles smash into each other, SHIP will direct them toward a fixed target, increasing the probability of detection. The method is expected to be 1,000 times more sensitive than any existing equipment at CERN. These ghost particles, potentially constituting dark matter or other unknown aspects of dark energy, remain invisible under ordinary conditions because of their extremely weak interactions with ordinary matter. The implications of the discovery of such particles are profound and will probably change our fundamental theories of physics. Along with SHIP, plans are underway for a future circular collider, which should be a leap forward in particle collision technology. It's planned that this collider will reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the future circular collider could open new chapters in the history of our universe. From advancing our understanding of fundamental particles to creating new technologies, the implications go far beyond particle physics, promising a glimpse into the very fabric of the cosmos, and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific achievements, the quest for knowledge is moving forward, promising a future in which the mysteries of the universe will be revealed one collision at a time. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan-3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the moon's south pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the Moon's South Pole, Chandrayaan-3 began its mission of exploration and discovery. So, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the Moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the Moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the Moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the Moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the Moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the Moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the Moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the Moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the Moon, and it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrayaan-3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity. It's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters at the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's south pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules. a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos. You've probably heard of dark matter, the elusive substance that makes up about 1/4 of the universe. That ghostly puppeteer is pulling the strings of the galaxy but never showing itself. But what if dark matter is just the tip of the cosmic iceberg? Imagine a universe where the scales of gravity tip in mysterious ways, where stars and binary systems, two stars orbiting a common center, defy the very laws established by Newton and Einstein. What if their equations are not the final word? Recent research suggests anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current understanding of gravity can fully explain. So, are we on the cusp of a paradigm shift? Is our view of the cosmos not as stable as we thought? In cosmic ballet, stars are the prima donnas that catch our eye. But have you ever wondered how these celestial luminaries come into being? It all starts in the dark, cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, pulling the particles closer and closer until they no longer resist gravity. They merge, triggering a nuclear fusion reaction that produces a star. However, the life of a star does not last forever. There comes a point when the nuclear fuel runs out, and the star faces its inevitable demise. For massive stars, this end is nothing short of spectacular. A supernova explosion that eclipses entire galaxies, if only for a short time. These supernovae are not just cosmic fireworks. They are the forges of the universe. It's in the crucible of these explosions that elements heavier than iron are created. So the gold in your jewelry, the calcium in your bones, it's all stardust. The remnants of a supernova explosion. But here's where the plot gets twisted. In a universe dominated by dark matter, these stars and their explosive deaths are part of a larger scene. Dark matter, with its gravitational pull, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, leading to a higher number of supernovae. In these galaxies, stars form and die at an accelerated rate, creating a dynamic and ever-changing landscape. Recent studies have even quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and the rate of star formation. But what if this correlation is not as simple as it seems? Enter MOND, Modified Newtonian Dynamics. This theory suggests that gravity behaves differently at very small accelerations. If Mond is correct, the high rate of star formation in dark matter-rich galaxies may have an alternative explanation. Double star systems, those cosmic pairs we discussed earlier, can serve as an ideal test laboratory for these theories. Their orbital dynamics can show whether Newtonian gravity persists or whether Mond offers a better explanation. As scientists delve deeper into the data, especially the treasure trove provided by the Gaia mission, we're getting closer to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often portrayed as a silent, mysterious entity that shapes galaxies but remains elusive. One of the most compelling theories attempting to solve this mystery is the cold dark matter model, or CDM. In the CDM model, dark matter is cold, which means that its particles move much slower than the speed of light. This slowness allows them to clump together to form the gravitational scaffolding on which galaxies are built. CDM-based computer modeling has been extremely successful in reconstructing the large-scale structure of the universe. It shows a cosmic network of galaxies connected by dark matter filaments that's very similar to what we observe. But, like any good story, there are unexpected plot twists. While CDM does an excellent job of explaining the grand architecture of the universe, it falters when we get closer to individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should drop sharply as we move away from the center. But observations tell a different story. The rotation curves remain surprisingly flat, suggesting that something else is involved here. Perhaps another kind of dark matter, or even a modification of gravity. And then there are dwarf galaxies, smaller satellites of larger galaxies like our Milky Way. The CDM model predicts many of these dwarf galaxies, but we just don't see as many as expected. These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where Mond enters the scene again, offering a different set of equations that better explain these galactic features. It's like two different scripts of the same movie, each with its interpretation of the main character, dark matter. At check weighing, the scientific community is divided. Is the CDM the final theory that unifies our understanding of the universe, or is it just a stepping stone toward a more complete model? For centuries, Sir Isaac Newton's equations have been the foundation of our understanding of gravity. They've been tested, retested, and retested, and have stood the test of time. But what if there is more to the story? Introducing Mond, or Modified Newtonian Dynamics, a theory that dares to modify Newton's sacred equations. It suggests that gravity behaves differently at extremely low accelerations, such as at the outskirts of galaxies. The goal of Mond, conceived by physicist Mordecai Milgrom in the early 1980s, is to resolve some of the inconsistencies that have arisen in our observations of galaxies, especially those puzzling rotation curves we discussed earlier. You see, Mond fits the observed flat rotation curves of galaxies perfectly, without resorting to dark matter. It's as if Mond is saying, wait, maybe you don't need to invent a mysterious form of matter. Maybe you just need to adjust your equations. And it's not just about rotation curves. Mond has also managed to explain the dynamics of some galaxy clusters, and even the large-scale structure of the universe, without relying on the mysterious dark matter. But of course, no theory is without problems. While Mond succeeds in some areas, it faces difficulties in others, such as explaining the cosmic microwave background afterglow of the Big Bang. The cosmic microwave background, or CMB, is a snapshot of the universe just 380,000 years after the Big Bang. The CDM model, with its dark matter component, explains the features of the relic radiation well. MOND, however, has difficulties here. And let's not forget our celestial pairs, double star systems. Recent studies, some of which we've already discussed, have shown contradictory results when applying MOND to double stars. So what does that give us? Well, at the very least, a state of exciting uncertainty. As new data comes in, especially from the Gaia mission, MOND continues to be hotly debated. Is MOND the missing piece of the puzzle that will finally explain the anomalies we observe? Or is it a useful but ultimately flawed stepping stone towards a more complete theory? In a universe full of questions, sometimes the answers lie closer to home. Just 1.5 million kilometers from Earth orbits Gaia, a spacecraft that may hold the keys to some of the universe's most puzzling mysteries. Launched by the European Space Agency in 2013, Gaia is no ordinary telescope. It's a space cartographer mapping the positions, distances, and motions of more than 1 billion stars with unprecedented accuracy. Imagine having the coordinates of 1 billion stars at your fingertips. It's like Google Maps for the Milky Way, but with a staggering level of detail. One of Gaia's key techniques is parallax, an ancient method with a modern interpretation. By observing a star from 2 different points in its orbit, Gaia can triangulate the distance to the star with incredible accuracy. But Gaia is more than just a space explorer. It's a theory tester. Remember those controversial theories about gravity and dark matter? Gaia data can be used to put those theories under the microscope. Take, for example, double star systems. These systems are crucial for testing theories like MOND. Gaia's precise measurements of the positions and velocities of these stars can help us understand which theory is correct. And it's not just stars. Gaia also observes asteroids, planets, and even distant galaxies. Its data have been used to refine the Hubble constant, a key parameter that helps us understand the expansion rate of the universe. Measuring the Hubble constant with Gaia has added a new twist to the ongoing cosmic controversy. Different methods yielded slightly different values, and Gaia's data became an important piece of this cosmic puzzle. But the Gaia mission is not without its challenges. While the spacecraft provides a wealth of data, interpreting that data is a different story. The same Gaia data have been used to both support and refute theories such as CDM and MOND, leading to heated debates in the scientific community. It's like a high-resolution photograph where everyone sees something different. Is it a speck on the lens or a revolutionary discovery? Interpretation depends on sophisticated statistical methods and, of course, on our basic assumptions about the universe. There is nothing more fascinating than double stars. 2 stars locked in a gravitational embrace, orbiting each other in a delicate balance of attraction and repulsion. As we mentioned earlier, these dual systems are not just celestial spectacles. They are cosmic laboratories. Here, in the intricate ballet of their orbits, we can test our deepest theories about the nature of gravity itself. Double stars have been a cornerstone of astronomical research for centuries. They've helped us measure the mass of stars, understand stellar evolution, and even confirm Einstein's general theory of relativity. But in the context of our ongoing debate between cold, dark matter and modified Newtonian dynamics, double stars play an even more important role. Their orbital dynamics can reveal whether Newtonian gravity persists, or whether MOND offers a better explanation. Recent studies have delved deeper into this question. Some studies, using data from the Gaia mission, have shown that double star systems behave as predicted by Newtonian gravity, casting doubt on the applicability of MOND. However, other studies tell a different story. They suggest that MOND is better suited for some double systems, especially those with large distances between them and weak gravitational attraction. Could it be that both theories are partially correct? Or are we missing a key piece of the puzzle? The scientific community is divided, and for good reason. The stakes are high. The behavior of double stars would either confirm our current theories or send us back to the drawing board in our quest to understand the universe. So, how do we weigh evidence? Meet Bayesian statistics, a mathematical framework that might just tip the scales. Named after Thomas Bayes, an 18th century statistician and theologian, Bayesian statistics offers a way to update our beliefs in light of new data. It's like a mathematical expression of the scientific method itself. Here's how it works. You start with a prior belief, or prior, which is your initial hypothesis. As new data becomes available, you update it before forming a posterior hypothesis, a revised hypothesis that better fits the actual data. In the context of our cosmic debate, be it cold dark matter, MOND, or something completely different, Bayesian statistics provides a rigorous way to assess which theory is more likely, given the observed data. For example, when analyzing double star systems, Bayesian methods can help quantify the probability that MOND, or Newtonian gravity, is the correct theory. It's not just about curve fitting, it's about estimating the weight of evidence. And it doesn't just apply to double stars. Bayesian statistics have been applied to a wide range of cosmic phenomena, from the distribution of dark matter in galaxy clusters to the rate of expansion of the universe. Nevertheless, Bayesian methods are not without critics. One of the most controversial points is the choice of a prior. How to choose the initial hypothesis in a way that does not distort the result. The choice of a prior can be controversial because it can affect the results. If your prior leans strongly towards one theory, a posterior may confirm that theory even if the other is equally true. As we grapple with these questions, Bayesian statistics remain a powerful tool in our analytical arsenal. It offers a way to make sense of complex spatial data, sift through the noise, and find the signal. The universe seems to refuse to reveal its secrets readily. Even as we gather more data, the debate about the true nature of gravity is intensifying. Hyun Che, an astronomer who recently hit the headlines, said, quote, "I was feeling like I was dreaming. It seemed so unreal. This is because my results did not match any previous results." Che's work stirred the pot by suggesting that when the gravitational acceleration of stars in certain double systems falls below a certain threshold, they're more consistent with MOND models than with the standard gravity model. But here's the rub. Che's findings contradict several previous studies. He mentions, quote, "One group has been claiming an anomaly for some time, but the anomaly seemed not to match well the predictions of existing modified gravity theories." This discrepancy in results is not just a glitch. It's a fundamental challenge to our understanding of the cosmos. It raises questions about the reliability of our models and the data we use to test them. So what does that give us? Well, at least a state of productive confusion. As Che concludes, quote, "Because the standard cosmology is based on general relativity, cosmology needs a major revision now." The debate is far from over. As we collect more data and refine our theories, the search for the ultimate truth about gravity and the universe continues. And in this quest, every anomaly, every contradictory result adds a new level of complexity and wonder. In the infinite depths of the universe lies a fundamental principle, as mysterious as it is omnipresent. This force governs the very fabric of existence, yet remains elusive to the casual observer. This is the story of entropy, a concept that reveals the hidden order in the apparent chaos of the cosmos. Here on Earth, entropy is evident in every rustling leaf, every rolling wave, and every moving cloud. It's the quiet organizer of natural processes, from the simplest to the most complex. But what is entropy really? It's a phenomenon often misunderstood as an ordinary disorder, but it's more than that. Entropy is a transformation, a movement from order to disorder, from concentration to dissipation. This is exactly why your coffee gets cold, why the ice melts, why the scent of flowers dissipates in the air. So let us understand how an order is hidden in what appears to be chaos, and how does this mysterious force shape our entire environment, from the smallest particle to the largest galaxy, and even the very course of life itself. There is a hidden force at work in every corner of our world, from the quiet forests to the bustling hearts of our cities. This force, often unnoticed, plays a key role in the great work of the universe. Imagine a dewdrop on a leaf, shimmering in the morning sunlight. As the sun rises, the dewdrop slowly disappears, and its particles disperse into the air. This phenomenon illustrates a fundamental principle of nature, the transition from a concentrated state, the dewdrop, to a dispersed state, the water vapor in the air. At the molecular level, this principle manifests itself as the tendency of particles to move from a state of concentration to a state of dispersion. This is similar to the way a crowd disperses after a concert, moving from a structured gathering to random scattered groups. In the center of our cities, this principle is reflected in the rhythm of daily life. The concentrated bustle of the morning rush hour gradually fades away as the day progresses. Entropy is often misunderstood as simple chaos or disorder, but it's much more nuanced than that. It's about transformation and change. Like a sandcastle slowly crumbling under the merciless waves, entropy is the inevitable transition from order to disorder. This concept is encapsulated in the second law of thermodynamics, a fundamental principle of physics. It states that in any closed system, entropy will either remain constant or increase over time. In other words, the natural course of the universe is toward greater dispersion and disorder. From the grand scale of the cosmos, where stars and galaxies form and disappear, to the minutiae of our daily lives. This principle is a universal constant. It governs the birth and death of stars, the flow of rivers, and even the fading heat in a coffee cup. Imagine a steaming cup of coffee left on a table. Over time, its heat dissipates into the surrounding air, cooling the coffee. This is entropy in action, redistributing energy from a concentrated state, hot coffee, to a more diffuse state, a cold room. Or take an ice cube melting on a warm day. The structured, solid form of ice turns into a puddle of water, whose molecules are free to move. This transition from a solid, ordered state to a fluid, disordered state is a classic example of increasing entropy. In every aspect of our universe, this quiet but relentless force is always present, subtly directing the flow of energy and matter. As we delve deeper into the theory, it's crucial to go back in time to the era when the concept first emerged. The history of entropy is intertwined with the minds of some of the most brilliant scientists in history. Our narrative begins with Sadi Carnot, a French physicist often referred to as the father of thermodynamics. In the early 19th century, Carnot was fascinated by the efficiency of steam engines, the driving force behind the Industrial Revolution. His research laid the foundation for the laws of thermodynamics, which were later incorporated into the concept of entropy. Carnot's visionary work described how heat engines work and focused on how energy is transferred and transformed. His theories have played a crucial role in understanding the dynamics of energy flow within systems. The next key figure in our story is Rudolf Clausius, a German physicist. Clausius was the one who introduced the term entropy in the mid-19th century. He built on Carnot's ideas by delving into the nature of heat and energy transfer. Clausius's work led to a more formal definition of entropy. He suggested that heat cannot spontaneously transfer from a colder body to a hotter one, the principle underlying the second law of thermodynamics. His mathematical formulation of this concept allowed it to be quantified, bringing clarity to its elusive nature. Another giant in this field was Ludwig Boltzmann, an Austrian physicist. Boltzmann's contributions in the late 19th century brought a statistical approach to thermodynamics. He linked the microscopic behavior of atoms and molecules to macroscopic properties of matter, such as temperature and entropy. Boltzmann's work was groundbreaking. He showed that entropy can be understood as a measure of disorder at the molecular level. His famous formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microstates, gave a profound insight into the nature of this phenomenon. The legacy of these pioneering scientists is immense. Their collective work laid the foundation for modern thermodynamics and statistical mechanics, fields that continue to evolve and shape our understanding of the universe. Turning our gaze to the natural world, we find that entropy is at work in every ecosystem, shaping the environment and the life within it. Nature, in its infinite complexity, is a vivid canvas of disorder in action. Consider a fallen tree in the forest. Over time, it undergoes a remarkable transformation. Microorganisms, insects, and fungi break it down, returning nutrients to the soil. This process of decay and renewal is a manifestation of our principle, reflecting the cycle of life and death in nature. Rivers are also agents of entropy. They constantly change the landscape, cutting through rock and soil, and redistributing sediments from the mountains to the sea. This relentless movement and transformation of matter is a classic example of the role of this principle in geophysical processes. Weather is another area in which chaos plays a crucial role. Cloud formation, rainfall, snowmelt. These are all processes driven by the distribution and redistribution of energy in the atmosphere on a global scale. In the oceans, entropy is manifested in the life cycles of marine ecosystems. Coral reefs, for example, thrive on the delicate balance of nutrient cycles, temperature, and ocean currents governed by the principles of energy flow. Photosynthesis, the process by which plants convert sunlight into energy, is another interesting example. Here, the entropy principle plays a role in converting solar energy into chemical energy, a process fundamental to life on Earth. From the tiniest interactions of microscopic organisms to the grandeur of ecological systems, this fundamental force is the invisible conductor of the natural world. It is the underlying principle that nurtures the beauty and dynamism of our planet. Life on Earth, in all its diverse forms, is deeply intertwined with the principles of energy flow and transformation. This complex relationship between life and energy reveals a universe in which chaos and order coexist in a delicate balance. Consider the simple process of seed germination. This process is a microcosm of life's ability to use and organize energy. As the seed grows, it absorbs energy from the environment, converting it into structured, organized forms. However, there's a price to pay for this organization, an increase in the overall disorderliness of the system. In the human body, Entropy is our constant companion. Our cells are energy conversion power plants, constantly converting nutrients into energy. This metabolic activity is vital to our existence, but it also leads to increased disorder as energy is released in the form of heat and waste products. Ecosystems are also valid examples. For example, in a rainforest, the flow of energy from the sun to plants and then through the food chain demonstrates the role of entropy in ecological processes. Each transfer of energy from one organism to another involves energy dissipation, contributing to the overall disorder of the ecosystem. Looking at the bigger picture, the evolution of life on Earth can be seen as a journey through entropy, from the first single-celled organisms to the complex network of life we see today. Evolution has been a process of increasing complexity, driven by the fundamental laws of energy and matter. In the grand narrative of life, entropy is not just a concept of decay or disorder. It's the driving force behind growth, complexity, and a constant cycle of transformation. Life in all its forms thrives in the delicate balance between order and chaos, a testament to the profound interplay of energy and matter. In the cosmic arena, the principles governing entropy show a universe in constant motion, a stage in which stars are born, live, and die in a great cycle of energy transformation. Star formation is a process of remarkable energy dynamics. Inside nebula, clouds of gas and dust collapse under gravity, heating up and eventually triggering nuclear fusion. It's a transition from potential energy to kinetic energy, a cosmic example of energy distribution on an enormous scale. The life cycle of stars can be seen as a narrative of energy transformation. In their final moments, massive stars explode as supernovae, dispersing their elements across the cosmos. This dispersion is a powerful demonstration of the universe's tendency to increase the dispersion of energy and matter. Black holes, in turn, represent one of the most intriguing aspects of cosmic entropy. These mysterious objects, which have such a strong gravitational pull that even light cannot escape them, play a significant role in the energy dynamics of the universe. The black hole event horizon marks the point of no return, where matter and energy are irreversibly absorbed, contributing to the overall disorder of the cosmos. By the way, our channel has already published a detailed video about the connection between black holes, Hawking radiation that depletes them, and entropy. We recommend you watch it. The expansion of the universe is itself a confirmation of these principles. Galaxies are diverging, energy is becoming more evenly distributed over vast space, and the fabric of the cosmos is stretching, all of which indicate that the universe is evolving toward a state of higher dispersion. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a glimpse into the early universe. As we know, this radiation is a remnant of a time when the universe was hot, dense, and in a lower entropy state. Paradoxically, as the universe expanded and cooled, its randomness increased. And this is what led to the inevitable formation of the complex structures we see today. One of the most profound consequences of these cosmic processes is the concept of the heat death of the universe. In this scenario, the universe reaches a state of maximum entropy, where all energy is distributed so uniformly that further energy transformations become impossible. This is a future in which the universe is cold, dark, and devoid of the energetic dynamics that drive cosmic evolution. In this vast cosmic action, the flow and transformation of energy shapes not only the stars and galaxies, but also the very destiny of the universe. It is a continuous process of creation, transformation, and ultimately, disintegration. In the modern world, the concept of entropy has transcended its scientific origins, finding applications in a variety of fields, but subject to common misconceptions. Currently, entropy plays a crucial role in the development of advanced technologies. In the field of renewable energy, a thorough understanding of this concept is essential to improve the efficiency of solar panels, wind turbines, and energy storage systems. This knowledge greatly helps in optimizing the conversion of natural energy sources into usable energy. In the field of information theory, entropy has acquired a new meaning. It represents a measure of uncertainty or randomness in a system. This concept is crucial in data encryption and compression, where controlling and predicting information patterns is essential. Despite its scientific importance, entropy is often misinterpreted. A common misconception is to equate entropy solely with disorder or chaos. Meanwhile, while the definition that entropy leads to an increase in disorder is correct, it is worth clarifying that we're talking about the distribution of energy and the probability of certain states. Another misconception is the notion that entropy can be reversed or overcome. In popular culture, we see images of time reversal or spontaneous assembly of objects. However, according to the second law of thermodynamics, in a closed system, entropy can only increase or remain constant. Modern physics research is considering its impact on quantum mechanics, the behavior of black holes, and the ultimate fate of the universe. Beyond theoretical physics, entropy has practical applications in environmental science, engineering, and urban planning. It helps to model climate change, design sustainable systems, and understand urban development patterns. The future will undoubtedly bring new challenges and opportunities, and our understanding of this phenomenon will be critical in addressing them. Whether it is advancing technology, exploring space, or managing our planet and conserving its resources, entropy remains a fundamental concept that will continue to define our journey into the unknown. In the field of space exploration, the James Webb Space Telescope is a beacon of human ingenuity and curiosity. Its recent incursion into the depths of our solar system has revealed discoveries that challenge the possibility of life beyond Earth. Among the many celestial bodies orbiting our giant neighbor Jupiter, Europa is a world of special interest. With its jagged surface and hidden ocean, this icy moon has long intrigued scientists and dreamers alike. However, it's the recent discovery of JWST that's brought Europa into the spotlight of astrobiological research. JWST, in an unprecedented observation of the Moon, has discovered carbon dioxide on Europa's surface. This discovery, while seemingly simple, has profound implications. Carbon dioxide, a molecule integral to life as we know it here on Earth, could be a marker pointing to the potential for life on extraterrestrial worlds. Let us together delve into the data obtained by JWST. What secrets does Europa hide beneath its icy facade? Could the discovery of carbon dioxide be a clue to life beyond Earth? Europa, a moon full of mystery, is a landscape both alien and fascinating. Its surface is covered in a canvas of ice with a complex network of lines and ridges. These features, known as lineae, are not just surface scars, but tell the story of the dynamic geologic processes taking place. This 9 to 15-mile thick ice shell hides a vast ocean that has interested scientists for decades. The lines on Europa's surface are believed to be the result of the ice crust interacting with the moon's underground ocean. These cracks and ridges form as the ice shifts and breaks, a process driven by Europa's motion around Jupiter. Beneath this frozen barrier is a salty ocean, estimated to be 40 to 90 miles deep. This hidden sea, dark and cold, is kept liquid not by solar heat, but by Jupiter's immense gravitational pull. So-called tidal deformations. The satellite rotates around its giant parent and generates enough heat to maintain the ocean's liquid state. The chemical composition of this ocean is the subject of intense research and speculation. It's believed that there may be hydrothermal vents on the ocean floor, similar to those found in Earth's oceans. These vents may provide the necessary energy and minerals to sustain life, making Europa's oceans a prime candidate for the search for extraterrestrial life. The physical properties of Europa's oceans also raise intriguing questions. The presence of salts and the ability to form complex organic compounds, combined with the energy of hydrothermal activity, create an environment in which life can exist. Ocean depths and pressures, although extreme, are not beyond habitability, as evidenced by life in the deep gorges on Earth. Europa's mysterious environment with its icy surface and ocean is an interesting case for research. But what exactly has attracted the eyes of scientists to this moon this time? With the help of JWST, astronomers have made an interesting discovery. Using data from NASA's Space Telescope, they've detected carbon dioxide on the icy surface of the satellite. This discovery is not just an addition to Europa's chemical profile, it's an important key to understanding the moon's potential for life. Using the near-spec near-infrared spectrograph, JWST has discovered carbon dioxide in the geologically young and chaotic Terra Regio locality. This discovery is not just about the presence of a molecule, it's about its origin. The carbon dioxide on the surface of Europa is thought to have come from within, from its mysterious underground ocean, rather than having been deposited by external forces, such as meteorites. This discovery suggests a dynamic exchange between Europa's ocean and its icy shell. The most interesting thing here is that carbon dioxide is unstable on Europa's surface, suggesting constant replenishment from the moon's interior. The presence of carbon dioxide in the young terrain region indicates a recent and possibly ongoing process. This exchange may hold the key to understanding ocean chemistry and, by extension, its ability to support life. This discovery was made possible by the near-spec JWST instrument, which provided detailed spectra of Europa's surface. The ability to pinpoint the location of specific chemicals, such as carbon dioxide, allows astronomers to build a more complete picture of Europa's chemical landscape. Each discovery adds a piece to the puzzle of this mysterious moon. But why is this gas being released? And even more so, how does this cosmic body remain warm, supporting a liquid subsurface ocean? Europa, in its gravitational interaction with Jupiter, experiences a phenomenon known as tidal deformation, or tidal flexing. This process, caused by Jupiter's enormous gravitational pull, is one of the key factors in shaping Europa's potential to harbor life. As Europa revolves around Jupiter, its shape is constantly bending. This constant bending generates significant internal heat, a process quite different from the solar heating that we're familiar with on Earth. This internal heating is critical because it's thought to keep Europa's underground ocean in a liquid state, despite the relatively low temperature of outer space. The heat generated by tidal bends may also stimulate geologic activity on Europa, such as subglacial volcanism and hydrothermal vents. These openings, if present, may be similar to those in Earth's deep oceans, which teem with life despite the lack of sunlight. The energy provided by tidal bends could be a crucial ingredient for life. In Earth's oceans, hydrothermal vents support entire ecosystems where life forms utilize chemical energy released from the Earth's interior. On Europa, a similar process could occur, with life forms potentially using the energy from hydrothermal vents to power their metabolic processes. In such an environment, life could exist independently of sunlight, relying instead on the chemical and thermal energy provided by Europa's internal dynamics. Carbon dioxide, a molecule so integral to life on Earth, now takes center stage in the discussion of extraterrestrial life. On our home planet, carbon dioxide is the cornerstone of the biological process of photosynthesis that drives Earth's ecosystems. But what role can this essential molecule play in the cold, alien environment of Europa? The discovery of carbon dioxide on Europa by the James Webb Space Telescope opens up intriguing possibilities. In extraterrestrial environments, especially on icy moons like Europa, carbon dioxide may play a different but equally important role in sustaining life. In the absence of sunlight, life in Europa's oceans will have to rely on chemical energy, a concept known as chemosynthesis. This is where carbon dioxide can play a key role. In Earth's deep oceans, some organisms use carbon dioxide combined with hydrogen from hydrothermal vents to create organic matter. This process, although independent of sunlight, is a fundamental aspect of life in extreme environments. The presence of carbon dioxide on Europa may indicate a similar process. If there are hydrothermal vents in Europa's oceans, as many scientists believe, these may be the very places where life forms use carbon dioxide, perhaps like Earth's deep-sea organisms. This leads to an intriguing question. Could the carbon dioxide on Europa's surface be a byproduct of biological activity in its oceans? While the topic remains speculative, such a possibility adds an exciting dimension to the search for life beyond Earth. The role of carbon dioxide in extraterrestrial biological processes is the subject of intense research and speculation. Its presence on an icy moon may be a marker indicating the potential for life in environments far removed from the sunlit world we know. So let's summarize. The key to Europa's potential habitability lies in three basic elements: liquid water, an energy source, and the necessary chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's subsurface ocean and the energy generated by tidal bends are consistent with the first 2 points, and the presence of carbon dioxide on its surface hints at the presence of the necessary elements. Detecting carbon dioxide on Europa is an important piece of the puzzle. On Earth, carbon dioxide is integral to life, playing a central role in photosynthesis and respiration. In the alien environment of Europa, this molecule may be equally important, potentially acting as a building block or part of metabolic processes for hypothetical life forms. The presence of carbon dioxide also suggests that Europa's environment is chemically active, a key factor in the search for life. This activity could indicate geologic processes or even hint at biological processes if life existed there. It's also only possible to emphasize the importance of studying Europa's ocean as a testing ground for understanding the origin of life. The conditions on Europa may be similar to those of early Earth, giving a rough idea of how life could have originated under extreme conditions. On Earth, carbon dioxide is a fundamental component of life, involved in processes such as photosynthesis and respiration. In the alien environment of Europa, this molecule could play a similar role, potentially serving as a building block for life or part of the metabolic processes of a life form. Carbon dioxide could be a byproduct of biological activity or a resource. As we stand on the threshold of a new era in astrobiology, the significance of the discoveries of the James Webb Space Telescope propels us into a future rich with possibilities. Upcoming missions to Europa, particularly the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, are designed to broaden our horizons and deepen our understanding of this enigmatic moon. NASA's JUICE mission, launched on April 14, 2023, aims to make detailed observations of Jupiter and its 3 large icy satellites, with a particular focus on Ganymede. However, the Europa survey will provide important data that will complement JWST's findings by providing insight into Europa's icy crust and its subsurface ocean. In turn, NASA's Europa Clipper, scheduled for launch in October 2024, is designed specifically to study Europa. Equipped with a suite of sophisticated instruments, this mission will conduct a detailed reconnaissance of Europa's ice shell and subsurface ocean in search of signs of habitability. The purpose of these missions is to build on JWST's groundbreaking discoveries, delve into the mysteries of Europa's environment. By scrutinizing Europa's surface, analyzing its ocean, and searching for biochemical signatures, these missions will improve our understanding of this moon's potential to support life. By the way, you still have a unique opportunity to be part of this historic exploration and get into the history of this remarkable moon. To quote NASA, join the mission and have your name engraved on NASA's Europa Clipper spacecraft as it travels 1.8 billion miles to explore Europa, an ocean world that may support life. Sign your name today to the message in a bottle. End of quote. Just imagine at a time when some people haven't even visited the next country, a piece of your personal history will travel such distances to orbit another planet. A truly mesmerizing thought. By adding your name, you're not just leaving a personal mark, you're becoming part of a legacy that will resonate in the annals of space exploration. Europa, once a distant and icy moon, is now the center of our quest to understand the existence of life beyond Earth. The JWST results, combined with future JUICE and Europa Clipper studies, usher in a new era of astrobiology. An era in which the search for extraterrestrial life is moving from the realm of speculation to reality. The solar system has served as a reliable bulwark for life. But one day, humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us even more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time, when it's impossible to take a photo of each one? Only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, even impossible task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet's satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future, and that is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method, or gravitational lensing, will not help to look for microsigns of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even techno-signatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome. In a universe filled with mysteries, one question towers above many others. Are we alone? This riddle, also known as the Fermi paradox, attempts to answer our understanding of the cosmos and our place in it. Named after physicist Enrico Fermi, who during a casual dinner conversation reflected on the silence of the universe. The paradox confronts us with a stark contrast. On the one hand, the sheer number of stars, like grains of sand on Earth's beaches, suggests a high probability of extraterrestrial civilizations. On the other hand, our sky remains eerily silent, devoid of any sign of these civilizations. Despite advanced technology and the ever-expanding reach of space, not a single whisper or wave has reached us from deep space. This silence raises profound questions. What are the barriers that prevent potential civilizations from reaching out or crossing the stellar expanse? Can the vast distances of the universe or the fleeting nature of civilizations explain their absence? Or does the answer lie in the very fabric of the emergence and survival of life in space? Among a sea of stars, our solar system provides a glimpse of the possibilities and limitations of life beyond Earth. Ice moons and distant worlds harbor oceans beneath their frozen crust, mirroring the early conditions in which life is thought to have originated on our planet. These hidden oceans, protected from the harshness of space, may be the cradle of life and intelligent beings. However, these creatures may very likely be incapable of traveling beyond their icy boundaries, or even unaware of such a possibility. Just such a hypothesis was recently proposed, forcing a rethinking of the variables of the Fermi paradox. Let's take a closer look at how much it's affected the answer to why we still have not been able to hear the echoes of alien civilizations in the universe. The silence that reigns in space is an enigma that has baffled minds for decades. Imagine a universe where technological marvels and interstellar communications fill the void between the stars. Such are the expectations of our science fiction and logical predictions based on the Drake equation, which estimates the number of active, sociable extraterrestrial civilizations in the Milky Way galaxy. However, when we delve into the vastness of space, the reality is strikingly different. The expected intergalactic discourse remains only an expectation. The Fermi paradox asks a deceptively simple question. There are billions of stars in the galaxy, many of which have Earth-like planets, but where is everyone? This fact has definitely caused perplexity among scientists and the public alike, leading to numerous theories attempting to solve this mystery. One common explanation is the Great Filter Theory, which suggests that at some point in the evolution from a planet to intelligent life capable of colonizing galaxies, there is a highly improbable step that few, if any, civilizations overcome. On the other hand, the Zoo hypothesis suggests that advanced extraterrestrial beings deliberately avoid contact with us to allow for natural evolution and socio-cultural development, much like zookeepers observing animals in a sanctuary. Strangely, despite our sophisticated antennas and listening devices, we've still not picked up the slightest whisper from space. This leads one to speculate that perhaps our listening techniques are not adapted to alien communication methods. Or worse, that intelligent life is extremely rare or short-lived due to self-destruction or cosmic events. Especially given the vast expanse of space we've already scanned, it's hard to draw any other conclusions. Why is this happening? It may suggest that our knowledge is incomplete now, or we're listening in the wrong way and at the wrong time. However, perhaps things are much simpler than they seem. One recent intriguing proposal is the fishbowl worlds hypothesis. The traditional search for extraterrestrial life often focuses on Earth-like conditions, planets in the habitable zones of their stars, with liquid water and atmospheres capable of supporting life as we know it. However, such a view can be too narrow and fail to take into account life that does not meet our Earth-like expectations. The fishbowl worlds hypothesis proposes a radical shift in the search for life. According to it, life thrives in subsurface oceans completely enclosed by a thick layer of ice. These worlds offer a stable environment protected from cosmic hazards such as radiation and meteor strikes, favoring the development and evolution of complex ecosystems in isolation. This theory draws inspiration from the work of scientists such as Alan Stern, whose contributions to space exploration have shed light on the mysteries of icy celestial bodies in our solar system. For example, the New Horizons mission discovered intriguing features on Pluto and its moon, Charon, that suggest the presence of subsurface oceans, as well as the possibility of similar conditions even in the colder regions of the Kuiper Belt. And in general, our solar system has moons such as Enceladus and Europa, orbiting Saturn and Jupiter, respectively. Geysers spewing water vapor and ice particles into space observed by instruments such as Cassini hint at a dynamic, active environment beneath their icy crust. But how do these icy moons and dwarf planets affect the fishbowl worlds theory? Well, the key lies in understanding the complex interplay of gravitational forces, radioactive decay, and perhaps even hydrothermal vents on the ocean floor, all of which may contribute to the creation and maintenance of subsurface oceans. In such an environment, life as we know it, or even life forms beyond our current understanding, could find a way to thrive, isolated but protected from the harshness of space by a thick layer of ice. In these secluded ecosystems, life could thrive without the ability to gaze at the stars or contemplate the universe beyond their icy confines. This begs the question, how could such isolated creatures communicate, or even imagine a reality beyond their own? This fact is definitely puzzling because it shatters our preconceived notions of what an advanced civilization might look like. On this basis, we can assume that the universe may be teeming with life hidden in such natural shelters. Perhaps our galaxy is full of these quiet, isolated worlds, whose inhabitants unknowingly share the cosmos with us. Beneath the icy shell of distant worlds, the concept of communication takes on a new dimension, far removed from our earthly perceptions. In these hidden oceans, life forms can develop unique methods of communication that are profoundly influenced by their secluded environments. On our planet, the ocean depths provide a glimpse of how life can adapt to the perpetual darkness of the subsurface. Marine species such as whales and dolphins use sound to communicate over vast distances of up to several thousand miles, a method that's efficient and effective in the dense environment of water. This terrestrial analogy suggests that creatures in the hidden oceans of icy worlds may also rely on sound or other forms of non-visual communication, negating the need for technology such as radio signals. In the absence of light, these creatures could have developed advanced echolocation abilities similar to those of cetaceans on Earth, allowing them to see through sound. Knowledge acquisition in this context would be fundamentally different, potentially focusing on nuanced acoustic information rather than visual or electromagnetic signals. It's quite possible that these mysterious beings, thriving in their secluded worlds, have a deep understanding of their environment, yet remain ignorant of the cosmos around them. However, the vast universe, with its myriad worlds, presents not only opportunities for life, but also formidable challenges for civilizations seeking to reach the stars. Among these challenges, the gravity of home planets is a colossal barrier to the dream of interstellar exploration. This aspect introduces another critical factor into the Drake equation known as the exoplanetary escape factor, which assesses the feasibility of space travel from worlds not like our own. Exoplanetary escape factor is an important addition to the Drake equation, offering a method for quantifying the difficulties an extraterrestrial civilization might face in trying to escape the gravitational grip of its home planet. The equation for the escape velocity of a planetary object shows that larger and more massive planets pose a huge problem. Earth, whose escape velocity is 11.19 kilometers per second, serves as a baseline for comparison. For instance, a hypothetical super-Earth with a mass much greater than our own would have a prohibitively high escape velocity, making conventional space travel an insurmountable task. Imagine the scale of engineering and energy required to break away from a planet far greater in size and mass than Earth. Escape velocity from such worlds would be much higher, requiring propulsion systems far beyond our current capabilities. Such worlds may be rich in life and even have advanced civilizations, yet remain eternally isolated and their skies eternally out of reach. These civilizations may develop in complete ignorance of the cosmos, and their technological advances limited to the confines of their own world. However, it is conceivable that these civilizations could explore alternative routes into space. Innovations such as space elevators, orbital rings, or even harnessing the energy of planetary rotation could provide solutions to the difficult problem of high flight speeds. However, these technological advances will require materials and energy sources far beyond what we currently consider possible. In addition, it further complicates the version about the development of life on icy moons and dwarf planets. Enclosed in a thick ice shell, these worlds provide protection and stable conditions for life, but they also create additional layers of isolation. For intelligent beings living in such environments, the very concept of space may be incomprehensible, hidden behind impenetrable barriers of ice and rock. It begs the question, how would these creatures perceive their place in the universe? And what colossal effort would it take for them to break through the ice ceiling and venture into the unknown? It would be logical to assume that in the heart of a world bound by the heavy chains of gravity or by a dense shell, the pace of life and the trajectory of civilization follow a lesser-known path. Here, the attention of intelligent life forms would be visibly directed inward, toward their world. In such societies, environmental constraints may lead them to focus on mastering their immediate surroundings, optimizing their habitat, and exploring their world in depth. In such a case, there's nothing strange about their lack of connectivity. Being able to go beyond their planet is necessary for the concept of going into space to be a foreign idea, both figuratively and literally. Now, as we stand on the threshold of a new era in space exploration, our eyes are turned not only to distant stars, but also to the icy guardians of our own solar system. Several ambitious missions will be heading to this icy expanse in the coming years. Europa Clipper, scheduled for launch this October, targeting Jupiter's moon Europa. Dragonfly, planned for a 2028 departure to Titan. And several proposed concept missions targeting Saturn's moon Enceladus are at the forefront of this search. These celestial bodies, once considered frozen wastelands, are now seen as prime candidates for the search for extraterrestrial life in our solar system. These missions are equipped with advanced technology to penetrate ice sheets and explore the vast oceans beneath them. By analyzing the composition of water plumes ejected into space, studying the geology of the ice, and mapping the subsurface oceans, scientists hope to find signs of life, or at least the conditions necessary for it to exist. In any case, so far, there's no direct evidence of extraterrestrial life in our system. However, in the next decade, this veil will be opened and will shed new light on this issue. The data collected may provide empirical support for the idea that life can exist in conditions far different from those on Earth, and that the universe may be teeming with invisible life, much of it hidden in such isolated fishbowl worlds. However, if we find nothing, we may have to scrap the idea and start looking elsewhere for clues. One thing is clear: our search, whether it uncovers vibrant alien ecosystems or stark voids, will forever change our cosmic perspective, propelling us into the next chapter of human discovery. Imagine a colossal object 6 miles wide, hurtling through space at 12 miles per second toward Earth. And it's not science fiction. 66 million years ago, such an asteroid slammed into what's now the Yucatan Peninsula, forming the crater Chicxulub and triggering a mass extinction event. Today, our planet continues to be threatened by near-Earth objects. These include asteroids and comets, whose orbits bring them into our space neighborhood. NASA and other space agencies have made significant strides in tracking and understanding these potential threats, but the risk remains. Advanced technology is at work to monitor and mitigate these threats. From kinetic strikes to gravity tractors, humanity is developing strategies to protect our world from these stellar invaders. But what would happen if another Chicxulub-sized asteroid was on a collision course with Earth today? How prepared are we for such a catastrophic event? Join us to learn planetary defense, the history, science, and the future against such impressive threats. So 66 million years ago, an event occurred on Earth that was so catastrophic that it changed the course of life on the planet. The asteroid, about 6 miles in diameter, slammed into the Yucatan Peninsula in present-day Mexico, forming what we now call the Chicxulub crater. The immediate aftermath was nothing short of apocalyptic. The collision released energy equivalent to billions of nuclear bombs, caused forest fires and tsunamis, and threw huge amounts of debris into the atmosphere. The impact's most significant and long-lasting effect was the release of dust, soot, and sulfur aerosols into the atmosphere. These particles created a global cloud that blocked sunlight for an extended period, a phenomena often referred to as impact winter. New research has shed light on the critical role of fine dust particles in this cataclysmic event. A study published in Nature Geoscience in October 2023 found that fine dust, particularly particles between 0.8 and 8 micrometers in diameter, played a significant role in abrupt climate change. The researchers collected 66 million-year-old rock samples from North Dakota, located an impressive distance from the impact site, which contained surprising amounts of these fine dust particles. These particles lingered in the atmosphere, forming a dense cloud that persisted for up to 20 years, with the first 5 to 8 years being the most severe. This long period of darkness led to a significant drop in global temperature, estimated at more than 18 degrees Fahrenheit, 10 degrees Celsius in the first year alone. As sunlight was blocked, photosynthesis stopped. Plants unable to produce food began to die out. This collapse of plant life had a cascading effect on the entire food chain. Herbivorous dinosaurs that relied on plants for their food, faced starvation. Consequently, the carnivorous dinosaurs that preyed on them also died. This chain reaction led to the extinction of about 75% of all species on Earth. Interestingly, the new study highlights the hitherto unnoticed impact of dust compared to soot and sulfur, which were previously thought to be the main culprits for the prolonged cooling period. The findings suggest that while soot and sulfur blocked sunlight more effectively, the sheer amount and persistence of dust had a profound and lasting impact. The study also provides insight into how some species managed to survive this dark period. Hibernating plants and animals had adaptations that allowed them to survive the prolonged lack of sunlight. However, the study casts doubt on the survival mechanisms of freshwater organisms, indicating that more research is needed to fully understand the specific mechanisms of death following a Chicxulub strike. So what are near-Earth objects? NEOs are asteroids, comets, and other celestial bodies whose orbits bring them close to Earth. These objects vary in size, from small, harmless rocks to massive bodies capable of causing a massive catastrophe. Asteroids are the rocky remnants of the early solar system, mostly found in the asteroid belt between Mars and Jupiter. Comets, on the other hand, originate from the outer regions of the solar system and are composed of ice, dust, and rocky material. As they approach the Sun, they develop luminous comas and tails. The danger posed by these objects depends on their size and trajectory. Although most NEOs are too small to cause significant damage, some, such as the Chicxulub impactor, are capable of causing global catastrophes. To mitigate these risks, space agencies such as NASA and the European Space Agency have developed extensive programs to track and detect NEOs. Telescopes around the world are constantly scanning the sky, and cataloging objects that are approaching Earth's orbit. One of the key instruments in this work is the Wide Field Infrared Survey Explorer, which has been repurposed for the NEOWISE mission. Hundreds of near-Earth asteroids have been discovered and characterized using this space telescope. The role of artificial intelligence in detecting unobserved asteroids is becoming increasingly important. In May 2024, an AI-based algorithm known as Trackless Heliocentric Orbit Recovery, or THOR for short, detected more than 27,000 previously unobserved asteroids in archival telescope images. This artificial intelligence tool analyzes huge amounts of data, identifying and tracking objects with remarkable efficiency. It can process up to 1.7 billion points of light in a single telescope image, connecting them into asteroid trajectories. The Vera C. Rubin Observatory, due to begin operations next year, will further enhance our ability to detect NEOs. Equipped with advanced artificial intelligence software such as HelioLink 3D, this observatory is expected to catalog millions of asteroids in its first few months of operation, doubling the current known population. While no near-Earth object is large enough to destroy the planet itself, asteroids of 1 mile or more in size can cause global catastrophes. For this reason, NASA has been tasked with detecting and tracking these large NEOs. As of 2021, NASA has detected over 90% of the largest objects, ensuring that none of them pose an immediate threat to Earth. However, smaller objects, while not as catastrophic on a global scale, can still cause significant regional damage. Take, for example, Apophis, named after the Egyptian god of chaos and destruction. It's a near-Earth asteroid that's captured the attention of scientists and the public. Discovered in 2004, this 1,000-foot wide or 304-meter wide asteroid initially caused concern because of calculations suggesting a possible collision with Earth in 2029. However, further observations have ruled out this possibility, confirming that Apophis will pass our planet safely. On April 13, 2029, Apophis will make an incredibly close approach to Earth, passing within 30,000 miles or 48,300 kilometers of our planet. By comparison, this distance is closer than the orbits of our few high-altitude satellites. This close pass provides a unique opportunity for scientific observations and research. During the flyby, the asteroid will become visible to the naked eye in some regions, appearing as a bright, moving point of light. This rare event will allow scientists to study its size, shape, and composition in unprecedented detail. NASA's Goldstone Deep Space Communications Complex in California will play a crucial role in observing Apophis. Using radar, scientists hope to gather detailed information about the asteroid's surface features and rotation. In addition, the NEOWISE mission can provide additional observations by focusing on Apophis' surface roughness and composition. These data are invaluable as they'll help refine our understanding of near-Earth asteroids. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, will make a close approach to Apophis during its shortest flyby. The mission's goal is to study the asteroid up close, providing detailed observations that ground-based telescopes cannot achieve. OSIRIS-APEX will collect data on the composition and surface structure of Apophis, as well as any changes that occur as it passes near Earth. The spacecraft's instruments will help determine the asteroid's internal composition, which will also contribute to our broader understanding of the formation and evolution of the solar system. The close passage of Apophis has also attracted the attention of international space agencies. Teams from all over the world plan to observe and study the asteroid using ground and space telescopes. As part of the Neolite project, researchers from the Julius Maximilians Universität in Würzburg have proposed several concepts for small spacecraft that could accompany Apophis during its flyby. One proposed mission includes a small satellite that would follow Apophis for 2 months, acquiring high-resolution images and measurements. Another concept combines a small satellite with the European Space Agency's planned Ramses mission, which would provide extensive scientific observations. Although the asteroid poses no immediate threat to Earth, its close approach in 2029 presents a great scientific opportunity. Studying this asteroid up close will greatly improve our planetary defense strategies. To protect Earth, scientists have developed several planetary defense mechanisms, each designed to prevent potential collisions. One of the main methods is the kinetic impact strategy. It involves sending a spacecraft that will collide with an asteroid at high speed, altering its trajectory. This method relies on momentum transfer to move an asteroid into a safer orbit. NASA's 2022 mission Double Asteroid Redirection Test, or simply DART, was the first test of this method. The DART target was a small lunar satellite, Dimorphos, orbiting a larger asteroid, Didymos. As a result of the collision, Dimorphos' orbit was successfully altered, providing valuable data for future missions. Another proposed method is the gravity tractor. This method uses the gravitational pull of the spacecraft to slowly change the trajectory of the asteroid over time. By maintaining a stable position near an asteroid, the spacecraft's gravity can gradually alter the object's trajectory. Although this method's still theoretical and hasn't been tested in space, it is a promising approach for dealing with potential threats identified in advance. In extreme cases, however, nuclear explosions could be used to deflect or destroy an asteroid. In this approach, a nuclear device is detonated at a safe distance from the asteroid, vaporizing part of its surface and creating a recoil effect that moves the asteroid off course. However, this method is controversial because of the potential risks and legal implications of using nuclear weapons in space. To prepare for potential asteroid impacts, international space agencies regularly conduct simulations and drills. These exercises help hone detection, tracking, and deflection strategies. Planetary defense is a global issue that requires cooperation and coordination among countries. For example, in 2021, NASA participated in an international planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. The exercise simulated the detection of a fictional asteroid on a collision course with Earth, allowing participants to practice their response strategies. As we continue to develop and refine our planetary defense strategies, international cooperation, and technological advances, they'll all play key roles in protecting our world from space-based threats. These cooperative efforts are essential, especially as we learn more about the diverse nature of the objects that threaten us. Asteroids and comets are often viewed as different celestial bodies. Asteroids are like the rocky remnants of the early solar system, mostly from the belt between Mars and Jupiter. Comets, on the other hand, are aliens from the outer reaches of our system and are composed of ice, dust, and rocky material. However, there are also rare objects that blur the boundaries between these two categories, exhibiting characteristics of both. One such object is QN-173, discovered in 2005. This unique celestial body orbits like an asteroid, but behaves like a comet. Unlike ordinary asteroids, which are inert, QN-173 exhibits comet-like activity by ejecting dust and developing a long, thin tail as it approaches the Sun. QN-173 orbits the Sun every 5 years, spending most of its time in the outer part of the asteroid belt. However, as it approaches the Sun, it shows increased activity, similar to a comet. This duality makes 2005 QN-173 an interesting object for astronomers. In the summer of 2021, astronomers using the Asteroid Terrestrial Impact Last Alert System in Hawaii observed an object displaying a comet-like tail. Further observations by Lowell Observatory and the Zwicky Transient Facility confirmed this activity. The 450,000-mile or 720,000-kilometer-long tail suggests that the object is covered in icy material that sublimates when heated by the Sun. It's this process that turns the ice directly into gas, releasing dust and creating the characteristic tail. Interestingly, the narrowness of the tail indicates that the dust particles barely leave the core at extremely slow velocities. And this presents a mystery to scientists, as such slow velocities would not normally allow dust to escape the asteroid's gravity. One hypothesis is that the rapid rotation of the core may contribute to the dust ejection. In addition to unique objects such as 2005 QN-173, many other near-Earth objects pose a potential threat to our planet. The European Space Agency maintains a comprehensive risk list, cataloging objects with a non-zero probability of colliding with Earth. The list contains detailed information on the size, velocity, and collision probability of each object. It currently contains over 1,600 targets. The list of risks is sorted by the Palermo scale, a logarithmic scale that assesses the risk of collision based on an object's size, speed, and probability of collision. Objects with higher values on the Palermo scale pose a greater potential threat. Statistical analysis of these potentially hazardous asteroids shows that while most NEOs pose minimal risk, there are a few objects that require close observation. For example, the size and velocity of an asteroid have a very significant impact on its probability of impact and potential damage. Large asteroids, usually over 1 kilometer in diameter, are of particular concern because of their ability to cause global catastrophes. Fortunately, NASA and other space agencies have identified and tracked more than 90% of these large objects, ensuring that none of them pose an immediate threat to Earth. Smaller objects, while not as catastrophic, can still cause significant regional damage. Events such as the Chelyabinsk meteor in 2013 and the Tunguska event in 1908 demonstrate the potential danger of small asteroids. As we continue to discover and track NEOs and refine our planetary defense strategies, international cooperation and technological advances remain critical. By understanding the diverse nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations to come.